Hello. In today's lecture, we are going to discuss a very common topic. It's not very special. It's a familiar topic. It's very common, and I should say that it's quite interesting and does not offer much of problems to the students, either when they are working or in the comprehension of the lecture. Now, I have written. The lecture is integral calculus. Part of that is area under a curve. The area under a curve, the process is called quadrature. Quadrature is the name given to evaluating areas. So, we have, for example, anybody knows that the rectangle or a square has an area of x square? We say squaring. So, quadrature in German there is a word which is Quadratmeter. Quadratmeter is square meter. Okay. So, there is a linkage to a Latin origin, of course I am sure. And what we will do is we will run through the various formulas for finding areas in Cartesian coordinates, in polar coordinates, but we will see or try to see that we keep the same geometrical situation so that the ultimate results are the same whether we integrate through parametric integration or Cartesian integration or polar integration. The ultimate result should not be dependent on the process. So, we for example concentrate on a very simple geometrical figure, that's a circle. We are trying to find the area of a circle, its perimeter and so on. Now, finding perimeters of course is a different basket, and we will of course cover that in a separate lecture. That's called rectification. Rectification is the name given to finding arc lengths. Rectification is the name given to finding arc lengths, lengths of curves from a certain point on the curve to another point. We will discuss all that in small steps. We are not likely to forget what we are planning to discuss. So, the important thing is to note that this is part of integral calculus and we are on the subject of quadrature. Now, first let me draw an arbitrary curve, an x-axis, a y-axis and an arbitrary curve. It's very simple to draw. Supposing we have a y-axis like this and the x-axis like this that runs horizontally. This is the origin. This is part of a curve whose equation is given in the form y is equal to fx. That functional description is given very clearly. For example, y is equal to x square or y is equal to the square root of x and so on. Now, we draw two vertical lines. This point is x is equal to a and this point is x is equal to b. We wish to find the area of this curve. Now, definite integrals of the form a to b fx dx, and we have done the definite integral from the point of view of definition and evaluating definite integrals of certain elementary functions by using that definition. Now, that has been covered in a separate lecture. Now, what we wish to do here is to say two things. This can be represented by capital FB minus capital FA. In other words, this fx is such that it is the derivative of capital Fx. So, I can write here fx is such that it is the d dx of capital Fx. So, what happens is when we integrate this function with respect to x, we will get capital Fx, which is called an antiderivative. It is called an antiderivative because the set of all antiderivatives is nothing but capital Fx plus a constant, which is an arbitrary constant of integration. That is number one. Number two, this formula is called the fundamental theorem of the integral calculus. It is due to Carl Friedrich Gauss. We may have mentioned his name in other lectures, but it doesn't matter if we learn important items again and again. It might appear in 2 or 3 lectures, it's fine. So, the fact that small fx integrated from a to b gives capital AB minus capital Fa, where capital Fx is an antiderivative like this, is the fundamental theorem of integral calculus. Okay, that's number one. Number two, we wish to give the area element and then find it. Now, let's see. We draw a vertical strip. We draw a vertical strip here, and it has a strip width of dx. This point is x, y, and y is fx. So, we can designate this point as x and fx. Now, it will be very clear that this strip area can be represented by simply this ordinate y, which is fx, into dx. So, we can write shaded area of strip shown in the figure is nothing but y dx, which happens to be fx dx. That's fine. So, this is just a strip area, and all of us know that integration is a process of infinite summation. That is where calculus deviates from discrete mathematics, which of course we put it in a different way. When I am asked what is calculus, I say it is the algebra of infinitesimal quantities. That means the quantities are very small. We have to sum thousands and millions and billions of small strip areas to generate this area, and that is the process called integration. That is the process called integration. So, it is easy to see that the area of this region that we shaded, now we will shade it again with a yellow set of lines. So, we are talking of the area A, B, C, D. It is a very well defined area. It has 4 boundaries which we must realize. The boundaries are: number 1, the x-axis; number 2, a part of the curve of y is equal to fx. So, that is the upper boundary, the lower boundary is y is equal to 0, and the ordinates erected at x is equal to a and x is equal to b. These are the 4 boundaries, and the area given or the area required is given not by summing up strips of finite width, but by this integral. We write it as a is integral a to b fx dx. That is what exactly we do. It's very easy to understand and comprehend why the area turns out to be integral y dx or fx dx. This can also be given in a different way. I'll come to that later. Before that, I'd like to do one problem, and that depends on a little bit of knowledge of integrals, which all of us have had in the past. Now, as an example, we take a very familiar curve for which, of course, we know the result. We know the end result. So what we do is we take a y-axis once again, an x-axis running horizontally, and we take it's no good, doesn't look like a circle. We want to take a quadrant of a circle, so we perhaps do something like this. Yeah. This is fairly good enough. We have drawn the quadrant of a circle. This is the origin, this is the y-axis, this is the x-axis, and here we have a quadrant of a circle. Now, this is part of a circle whose center is at the origin and whose radius we will assume is a units. If the radius is a units, from O to A is a units, from O to this point, if we call it B, is also a units. Now, we've learned in high school when we did circles that the equation of a circle is given by x square plus y square is equal to a square. If its origin is at the center, if its center is at the origin and if its radius is a units, this is indeed the area of a circle. So, we are going to evaluate the value of the integral y dx from x is equal to 0, all the way up to x is equal to a. And if we are able to do that, we will have in our hands the area of one quadrant of a circle, and that is shown here. So, we will rub out the diagram. Maybe we can do a bit of work here, let the diagram be alive. Now, here what we have to do is integral 0 to a y dx. This implies that my y square is a square minus x square, and that implies, my friend, y is equal to under root of a square minus x square. That's fair enough. So, when we write y dx, we have every right to write that the required area is 0 to a under root a square minus x square dx. So, we have brought down the entire problem just to the point where we have to evaluate a simple integral, and I again go back to mathematics of class 11, 12, and we know that this can be integrated by using a substitution, which I will put up there. We will put up the substitution to evaluate this integral. The presence of under root of a square minus x square is suggestive of the fact that we can use a substitution x is equal to a cos theta or x is equal to a sin theta. Now, we use the following substitution: x is equal to a sin theta, that implies dx is equal to a cos theta d theta. This is fine. Now, one has to change the limits of x from 0 to a to corresponding limits of theta. Now, when x is equal to a, upper limit, sin theta will become equal to 1, and theta therefore will correspondingly be pi by 2. So we write theta upper limit is pi by 2 and theta lower limit is 0, because when we put in this substitution x is equal to 0, which is lower limit, a is finite, so sin theta is 0, that leads us to theta lower limit is 0. Hence, after substitution, the required area, if denoted by, okay, we'll denote it by A for area, it's fine. A is equal to integral 0 up to pi by 2. This becomes a cos theta, because a square minus a square sin square theta is a square cos square theta. If we take the square root, it is a cos theta. So this is a cos theta. Dx is a cos theta d theta. So we write a cos theta d theta. So once again, what do we have? We have to evaluate an integral 0 to pi by 2 a square cos square theta d theta with respect to theta. Once we can get to that integral, the value of that integral, we have in our hands the area of one quadrant of a circle. We will draw out everything and just do the last two steps of the integration. This is also not necessary, so it goes straight away. So this is equal to a square 0 to pi by 2. This is not minus or anything, this is just a cos square theta. That is a square by 2 into 2 cos square theta d theta 0 to pi by 2. That is a square by 2. Now 2 cos square theta 0 to pi by 2. 2 cos square theta we know is 1 plus cos 2 theta, because cos 2 theta is 2 cos square theta minus 1. So if you write cos of 2 theta is 2 cos square theta minus 1, then cos square theta is 1 plus cos 2 theta, or 2 cos square theta is 1 plus 2 cos theta. So we write this as becoming equal to a square by 2 integral 1 plus cos 2 theta d theta 0 pi by 2. Now this is very simply this is a square over 2, integrate the 1, you get theta, integrate cos 2 theta, we get sine of 2 theta divided by 2, trapped between 0 and pi by 2. Now we evaluate, keeping this outside. For this upper limit, this gets pi by 2 value and this becomes 0, because sine of pi 2 theta is 0. For the lower limit, each of the terms vanishes. So we have a square by 2 into pi by 2. So the net result is pi by 2 a square by 2, which is pi a square by 4. But this is expected because we want to get the area of a quadrant. The area of this circle, the whole circle, is 4 times the area of this. So if you multiply this by 4, 2 and 2 gets knocked off, and what remains is pi a square. This is perhaps the first time, or no, I shouldn't say first time, in class 12 you have encountered this once, that you have started to believe what you learnt in class 7 or 8 or 9, that the area of a circle is pi r squared. Excuse me. In those days, if you were to ask your teacher what is this pi, they would have certainly said it is a mathematical constant and has a value of 22/7. So, if the radius of any circular figure is known to be a units, then the area of that entire circle is pi into a square, with the value of pi taken as 22/7, or to a first approximation as 3.14. So, that is what I want to conclude this part of the lecture with. We will carry on with other forms of integration, other forms of equations.